Okay, this is the second video in the playlist that deals with drawing Lewis formulas of molecular compounds. A Lewis formula is a structural formula, so it shows the connectivity between atoms. And so what I want to do in this video is actually start the process and take the viewer through a set of simple rules to convert a chemical formula of a molecular compound. So remember that structural formulas are specific to molecular compounds, and what I want to do is take the viewer through a list of simple rules to convert a chemical formula into a structural formula. So we're going to start with water because generally speaking I think it's a molecule that no matter what level of chemistry student you are, it's likely that you've seen it before. And so I want to do something that people are familiar with. Now, before we get started into this, there is one thing that I want to address. So in the last video, we talked about the issue that the bonds in a molecular compound, which we show as dashes, are covalent bonds. All right. And in a covalent bond, electrons are shared. As we learn to draw these molecules, the crucial thing for you to understand is that when atoms combine to form covalent bonds, they utilize their valence electrons. So this whole process is dependent on valence electrons. All right. So what we're going to do when we start to proceed into drawing these structural formulas is we're going to sum together the total valence electrons from all the atoms that are involved in the molecule. All right. So it's the valence electrons that are used in order for atoms to come together and form covalent bonds, and it's the valence electrons that are going to be involved in the covalent bonds. This will be the dash. All right, and it's the valence electrons that are involved in the unshared electrons. So remember that we've got two kinds of electrons in molecules. We have the unshared pairs and we have the bonding electrons. So the dashes represent bonding electrons. All right. So let's go ahead with that bit of a review and draw the first molecule. So what we're going to do is literally we're just going to draw water, because what I want to do is take the viewer through the rules that, or the steps rather that we use to do this. All right. So step number one, when converting a chemical formula into a structural formula, will be to count total valence electrons available. Count total valence electrons. All right, so we look at hydrogen, or we look at H2O, and we see that there are two H's in here. All right, and there's one oxygen. And how do we find the valence? All right, so this is where you're going to be utilizing a periodic table. Remember that your group number, okay, and that's the number that I've written in blue at the top of each of these chemical groups. So the group number tells you the valence. So group number gives valence. All right, so we see for hydrogen that it's in group 1A, and therefore there are two valence electrons. So to count the total valence, there's two hydrogens. Each hydrogen has one valence electron. That's going to be added to the oxygen. So we come over here and we see that the oxygen's in group 6A. All right, and that means that oxygen actually has 6 valence electrons, and there's only one oxygen in water, so we write 6. The total is going to be 8 valence electrons. All right, 8 valence electrons. Now, as an aside, and I think I'm going to put this down here, remember that hydrogen, all right, if we were to write its electron configuration, is going to be 1s1, right? Here's your valence electron. That's the valence electron right there. And if we look at oxygen, its configuration's 1s2, 2s2, 2p4. All right, so oxygen's total outer valence is right here. I'm underlining it in red. And you see that the total valence is 2 plus 4 for a total of 6. This is where the group number comes from. All right, this is where the group number comes from. All right, now, so we've completed step 1 for this. Now, step number 2 is to draw what I call the skeleton structure. So draw skeleton structure. All right, and in this step, all you're going to do is basically identify the central atom, and I'll talk about that more as we go through this, but in H2O it's pretty obvious that the central atom needs to be oxygen. And then there are going to be 2 external atoms, which will be the hydrogens that are attached to the oxygen. So the beginner might do something like this, which is fine. We put the oxygen in the middle, and we put the hydrogens to either side, and there is a rationale in this where we want the outer atoms to be as far apart from one another as possible, because they've got these outer atoms that are going to have electrons in them, and we want those electrons not to overlap, because remember, electrons all have the same charge. You'll notice in the molecule that I drew up here that the hydrogens are actually bent downward, and that's because I already understand, or when I look at this structure, I already know what the shape of the molecule is, and a beginner is not going to know that. So this is fine to do it this way, or you can do it the way I did it, where you draw the hydrogens down if you've got a little bit more knowledge. All right. Now, once we have the skeleton structure, so we've put the outer atoms around a central atom, then the third thing that we're going to do now, all right, is we're going to connect central atom to outer atoms using dashes. Remember that one dash, all right, is one bond. All right, so we're going to come in here and we just go ahead and connect central atom to the outer atom. All right, now what we're going to do next is a quick electron count, and I think I'm just going to put that in here. Do quick electron count. And the issue here is just to see how many electrons we used, and we're comparing that back to the total number of valence that we counted, because for this ultimately for this molecule to be correct, the total electrons that we used is going to have to equal exactly the amount of electrons that went into this. So what I want to do right now is just find out how many we've used up. So we've used 2 electrons in this bond, and we've used 2 electrons in this bond, so our quick count is 4. And that means we've got 4 electrons left to go. Now, in step number 4, what we're going to do now is we're going to place remaining electrons as unshared pairs. Now, how do you do this? All right, so you're going to start with the central atom, and we're going, if we have electrons left over after we're done with the central atom, then we're going to move to the outer atom. How do we know when we're done with the central atom? The key is to have not more than 8 electrons on any given central atom. So I'm going to go ahead and add a pair of electrons here. Do your count. It's 2, 4, 6, and I'll put a pair of electrons here. All right, and we've got a total of 8 electrons. So let's just say, for the sake of argument, we actually had more electrons to go. Then what we would do at this point is move to the outer or the external atoms. And in this case, that's not going to happen, because if you look back at our electron count here, we've already used up the 8. Let me come over here and finish on this one. So we're going to put our pairs of electrons here. So to finish with this rule, I want to come back over here to our rule. All right, we're going to place remaining electrons as unshared pairs, and we move from central atom to outer atoms. Okay, maintaining no more than 8 electrons. No more than 8 electrons. All right. So now we've done that here, and now we're going to move to the 5th rule, which I'm going to put up here, or the 5th step. And this is the test step. This is where we evaluate what we've done to see if we have actually accomplished the best structure. All right. And there are going to be 2 steps to this, and I highly recommend doing them in order. Although, so yeah, I highly recommend doing them in order. The first thing is to count total electrons. And electron count the electron count has to equal the total valence from number 1. All right, and then part B, you must have you must have 8 electrons around period 2 elements, and that includes carbon, oxygen, nitrogen, and actually 7A atoms. So I extended this a little bit, not only period 2, but also going down this group 7A. All right, so now when we come back over here to our molecules, and this test is very, very important, especially part A. So what I do is I count up how many total electrons I have in this structure. All right, and there's 2, 4, 6, 8. There's 8 total electrons in this structure. And what's important here is to compare this number back to the original count. These 2 numbers have to be equal, and if they're not, then the structure you drew, no matter how beautiful it is just plain wrong. So that's the first thing you need to do when you finish the structure. You need to count the total electrons that are in it. Make sure that that matches exactly the total number of valence electrons that went into the structure. And as long as those 2 numbers are the same, then you know that you've met that very important step. All of the valence electrons have to be used. All of them have to be used up. Now, the second part of it is to make sure you've got 8 electrons around the period 2 elements, mainly carbon, oxygen, and nitrogen. So we come back into our oxygen in both of these cases here, and we make sure that we've got 8 electrons around each of those oxygens, and we do. So basically we've met what's called the octet rule. That's what this is. B is the octet rule. And then the hydrogen is important because you need to realize that for that, there never can be more than 2 electrons next to a hydrogen. So you want to just make sure that you didn't glitch and actually try to bond hydrogen to more than one atom. So duet rule for hydrogen, only 2 electrons. All right. So in this video, what I've tried to do is give you the basic beginning of how to do this. And there are more steps, but what we're going to do is close here, and I'll go to a third video where we're just going to practice this with very simple molecules.